So a very good afternoon and a very warm welcome to this live session on digital signal processing and its applications. I do hope that all of you are able to hear. Can you say something on the chat? Those of you who are here, can you hear us and see us? So I have my young friend here, my teaching associate, Aniket Sadashiv, also sitting with me. And today we are going to answer your queries and address your concerns and talk to you in this live session. So can we have an introduction from all those who are on the live session now? You can talk in the chat and please put forward your questions or queries or whatever. Yes. So welcome, Satish Kumar. Good afternoon. So would you like to ask us something, Satish, or discuss something? Take some time for the... Can you hear us, Satish? Do confirm that you're able to hear us and see us. And then please put up whatever you wish to share. Yes, hello, Chikyal Neetu. Good afternoon, Neetu. Can you hear us and see us? Yes, Satish. So why don't you share what you wish to with us that we can respond? Neetu as well. Yes. Okay, hello, Krishna Koneru. You're a retired IT professional. Oh, I see. You're a retired IT professional and mechanical engineer by degree. I'm learning communications. And I'm glad to know that you find our lectures very friendly and intuitive. Do you have any questions or anything that you would like us to discuss today? Krishna Kuneruji? Meetuji, do you have anything that we would like, we should address? Yes, please, Krishna. Can you speak? I don't know. Can you speak? It seems that I don't know if you can speak, but you can put up your question. You can type in there. Can we allow him to talk? I don't know, but he can't. Unfortunately, we don't have a mechanism to allow you to put up your audio or video. But we can receive what your see. So we can receive. Okay, now I have a question. How do we use IIR filters and adaptive signal? See, when you want to use IIR filters in adaptive signal processing, then the mechanism is very different from what you do with FIR filters, right? Now, one way to do this is to use the lattice structure. For IIR filters, one way is to use the lattice structure, because when you want to adapt the filter, you have to ensure that the filter does not become unstable. So if you're using the lattice structure, then the lattice parameters can be monitored to be less than 1 in magnitude. And you can adapt within that region. you adapt, of course, so as to minimize some quantity, maybe the least squared error. This is for Neetu-ji. But then you have to monitor the lattice parameters to remain less than 1 in magnitude. So if you wish to use IIR filters in adaptive signals, in adaptive signal processing, then it's best to use the lattice structure. Is that what you have in mind, Neetu-ji? You can answer. Meanwhile, Krishna Koneru-ji is posted in the Google sheet. But Krishna Koneru, maybe it's a good idea for you to also post it here, so everybody knows. Or, put up the question, or just copy and paste the question here. Okay, so Neetu is satisfied. Okay. So Krishna Koneru-ji, you can just copy and paste the question here. That's better. Okay. All right. So let me take Satish Kumar's question meanwhile. So he says he's studying in the 3rd year of the C branch. He wants to know how his core subjects are used in the real world in a detailed manner. Okay, Satish Kumarji, what are your core subjects right now? Give me some examples of what core subjects you've learned, and I will answer one by one. And while you put that on the chat, I will respond to Krishna Koreju's question. He says for FIR filters, there are no poles. You're right. FIR, well, the only pole which FIR filters could have is a pole at 0, at Z equal to 0. If it is a causal filter, it's going to have a pole at Z equal to 0. It's going to have multiple poles at Z equal to 0, right? But otherwise, the FIR filter is unconditionally stable. Its poles are only possibly at Z equal to 0. And if the FIR filter is non-causal, it could have poles at Z tending to infinity. So the poles can only be at Z equal to 0 or Z tending to infinity, right? So, it depends. If it's a non-causal filter, then in either case, the FIR filter is always stable. Anyway, you don't need to go to poles to see that. The impulse response is absolutely summable, and therefore the system is absolutely stable, is unconditionally stable in an FIR filter. All right. So meanwhile, I'll request Satish Kumar to put up his core subject so I can respond to his question. Is that your question, Krishna Koneru? If you have further questions, please paste them here so I can respond to them. Okay, good, Krishna Koneru. So you got your response. Do you have further questions? You can put them in the chat. Okay. All right. I'm also able to see the Google sheet. Now I'll take the questions one by one. So okay. So I have a question from Sharda. So kind request to explain how to solve first assignment question in assignment 5 and also question 5, 9, 10. You see, it's better you tell us. I don't know. We are going to cover. Okay. So, all right. So, Aniket Sadashiv says, my teaching associate who's with me right now says that they are going to give you a detailed explanation of this. But if you wish, I can give you some hints. But would you, it'll be nice if you're on the stage right now. Sharda, could you tell us what this question was? Do you remember what the question was? No. Okay. So, if you remember, if you're on stage right now, and if you can tell us what the question is, I can give you some hints to go about it. Let's take the other question which Sharda has. This one. Okay. Yeah, so I see there's a question which has been put up by Sharda. It says, in Xn troublesome input case, the definition of Xn equal to conjugate mod Hn, conjugate Hn by mod conjugate Hn. Can this be kindly explained on why? Okay, I'll explain that. You see, that now what is the troublesome input when you are trying to test the system for step? See, what are you trying to prove? Let me give a context here. See, what you're trying to show is that the impulse response, needs to be absolutely summable in order that the system be stable. If it's a linear shift invariant system, you need the impulse response to be absolutely summable. So it's a necessary and sufficient condition. You see, we showed that if the impulse response is absolutely summable, then the system being stable is not so difficult to prove. That it's a sufficient condition. Because, you can always upper bound your, if you have a bounded input, you can upper bound the output in magnitude if you know the impulse response is absolutely summable. That was one part of the proof which is relatively easier. But here you are trying to show the condition is necessary. That means you're trying to show. So, the question, I'll just, for the benefit of everybody who's in the audience right now, I'll just repeat what Sharda has asked. See, Sharda is asking, I had in the lecture talked about the necessary condition for stability of a linear shift invariant system. There, I said you need to give a troublesome input. I gave the story of the polyglot, I'll come to all the questions, So I gave the story of the polyglot who, knew many languages and you had to guess which language was his mother tongue. So that was, you gave a troublesome input to the polyglot so that he responded with certain fierce words in his own mother tongue. That was it. So here too, you need to give a troublesome input to this stable LSI system, which reveals the absolute summability of its impulse response. Now, this input, which Sharda has specified, namely conjugate Hn by absolute value of Hn, conjugate Hn. Now, see, this one really is an input which is troublesome because it has a maximum magnitude of 1. When applied to this system, it produces the absolute sum at a particular output sample. That was the idea. So it forcibly produces the absolute sum at a particular output sample. And then if the system needs to be, needs to produce a bounded input for a bounded output for a bounded input, then the input is bounded here. The input is bounded by 1. So the output needs to be bounded if you claim the system is stable for necessity. And that means that the absolute sum needs to be bounded. That is the idea. So this troublesome input is an input which has a maximum magnitude of 1 and which, when applied to the system, forces the system to bring out the absolute sum at a particular point, necessitating the absolute summability of the impulse response. So that is the idea. If it's not clear, you can ask me again and I'll clarify. I'll take one more. Now I have a question from Krishna Koneru. I think he's also put it in the chat. He's asked, what is the concept of negative frequency and zero-centered signals? What do they mean really? What when time and frequency are always positive? Good question. See, time is positive in the sense that time only moves in one direction physically. That in that sense, time is positive. Right? Time only moves. The movement of time only, we have not yet, I should say not yet, we have not yet come to any kind of mechanism of going backward in time. You can go backward or forward in space, up, down, anything, is it? Left, right. But you cannot go backward in time. So time is unidirectional in its motion, in its progression. In that sense, that is a restriction on time. Not that, see now, where you put your reference in time is up to you. So you can put your reference somewhere in the future also. And then all that we are seeing now is at negative time with respect to that reference. So time, it moves, progresses in one direction, but the reference is up to you to choose. You can choose the reference as you like. And that reference would be called 0. With respect to that reference, you can have positive or negative values of time. Okay, so that is the idea that one has to understand. Now, you see, it's also important to understand what you mean by zero-centered signals. Now, actually, if you have, see, in principle time, we don't know the beginning of time, right? So you could in principle put any point as time reference and all the time before that, including times to which we do not at present have access, right? But conceptually it is there, will be negative time. All times which are after the reference will be positive time. And so in that sense you can have, and then you can have zero-centered signal. If it is, you can conceive of a signal which is symmetric around the reference. That becomes a zero-centered signal, all right? Now, frequency is positive when you think of it as the frequency of a sinusoid. But every sinusoid is created by two oppositely rotating phases. So these two oppositely rotating phases respectively have one positive angular frequency and one negative angular frequency. So every sinusoid is associated with two oppositely rotating phases, one with a positive angular frequency and one with a negative angular frequency. So I hope that is why and the frequency axis that we talk about in the discussion on frequency response is this axis of phasor frequencies, the axis of rotating complex number frequencies, not the axis of sinusoidal frequencies. So is that clear, Krishna Koneru-ji? If not, you can put the question further, right? So now, while Krishna Koneru-ji responds, I'll also take up Satish Kumar's question. So he has given me, so he's a third-year student, in fact, you have your, I could answer the question. But, I'd like my young friend here, Aniket Sadashiv, to take your question. So he says, he has several subjects, analog electronics, digital signal processing, and many more, he says. And he is asking, how the subjects are used in the real world. So I'm sure I'll have Aniket. Aniket is a very good student of the 4th year. You're very lucky to have him as teaching associate. And, Aniket Sadashiv will now help you answer the question, because he's fresh, he's a young 4th year student, a very good student, very sincere student, he's doing very well in his academic program, and he's very committed to his studies. And he's also very resourceful in terms of what he does in practical applications and in applying his knowledge. So he's going to now first share with you his response to this question.
Yeah, okay. So for analog electronics, as far as real world things are concerned, all your amplifiers that you see, all the sound amplifiers, wherever you have to do something with real world signals, the analog electronics part comes into play. So in sound amplifiers, you're using analog signals. A lot of filters, transducers and all are related to the usage of analog electronics. As far as resources are concerned, like one of the resource which the book by Behrad Razavi on analog electronics, that I think every chapter begins with a real world example followed by the discussion on the material in that chapter. Also, he has a video lecture series named by Analog Electronic One or something like that. I think one is for MOSFET and one is using BJT. So you can refer to that on YouTube. It's freely available. Then similarly for digital electronics, like the laptop that we are using, the processors, all these microprocessors and all the internals of how this laptop is working, how this bits and all, that pertains to your digital electronics part. The finite state machines, how we encode, like how programs are written, the internals of that are essentially related to digital electronics. Again, for digital electronics, you can refer to book by Maurice Mano or by Zvi Kohavi or Neeraj Jha. All these are excellent books. And again, there are in general, if you want to find any book related to real world applications, you can just add real-time applications followed by the subject. You will actually end up with a lot of books related to that. Or even the first few pages or their introductions, they also cover a lot of applications in general. Then for digital signal processing, again, you can definitely search lectures are there. Then there's also a previous offering of signals and systems by a sir only on YouTube. If you search sir's name followed by signals and systems, you can find it. And as far as books are concerned, Oppenheim is there. His lectures are also there on MIT OpenCourse, he also goes in certain lectures to his labs and he shows things like aliasing using uh, a lot of experiments and stuff. So a few lectures, you'll see that he has covered real-time experiments in those lectures. So you'll definitely enjoy them. Yeah.
Very good. Thank you very much, Aniket. In fact, I'll add to what Aniket says. Sai, right now, Satish Kumar, right now, you and I are communicating. Do you know that right now we are using all the three subjects that you mentioned, right? Analog electronics, digital electronics, and digital signal processing. How are we using analog electronics? Why, I have several analog components sitting in this room from which I'm transmitting. As Aniket says, there are amplifiers, there are, in fact, there are also certain analog components. There are so many analog components inside this laptop, which we are using for communicating with you. There are several analog components which capture the picture here with a camera. So I'm sitting in a room where there are several analog components, right? There are, in fact, there are several analog components which transmit information to you in the form in which you're receiving it. And there are also several digital, of course, digital components in a computer, no shortage. There are so many digital components in a laptop. And therefore, digital electronics is right there. Now, when this video is being transmitted to you, you couldn't possibly see the video in raw form. It had to be transmitted in a more efficient manner. And this can only be done with digital signal processing. Once you process the data that's coming out of the video and transmit it with a more efficient utilization of memory, with a more efficient representation. So, for example, when you store this video on your disk, or if wherever this video gets stored, it can't possibly store in raw form. There has to be some kind of compression because data is huge. So a lot of digital signal processing goes in there. Okay, so many more. Satish, if you tell us the many more, then I can, then I can respond. Okay, now I'll take up Sharda's question a little later. I'll first take up Krishna Koneru's questions. So, Krishna Koneru says, negative frequency is only mathematical convenience. Well, as I said, the so-called negative frequency that we have there is a companion to a positive frequency, both of complex rotating phasors. Okay, so complex rotating phasors, both of them are complex rotating phasors. And one, you take a given sinusoid, given sine wave, as one so-called positively rotating complex phasor and one negatively rotating complex phasor. Now, if we say our bias tends to put the negative frequency as something that is created for mathematical convenience, but actually even the positive frequency here is just symmetric. It's also only for mathematical convenience. What is created for mathematical convenience here is not positive and negative frequency, but the fact that you're replacing the sinusoid with two phasors. The two phasors are created for mathematical convenience, right? So that is the way you should look at it. We don't discriminate the negative frequency to be just a figment of our imagination, right? The phasors themselves are figments of our imagination created for convenience. The sinusoids are real, right? But the phasors together, both the positive and the negative frequency, are either equally real as you see them or equally imaginary. Or imaginary meaning, I mean, they are only a figment of our imagination. Now, I'll take your second question. If it's not clear, please ask me again. Now, the second question is, digital frequency does not have units. Now, you have to see in the digital frequency, on the digital frequency axis, before you normalize, it has units. So, when you sample a signal, you draw the spectrum on the original Hertz axis. By taking the original spectrum, translating to every multiple of the sampling frequency and adding these. There you're still working with the traditional Hertz axis or kilohertz axis. After that, when you normalize this axis to the sampling frequency, meaning you put the sampling angular frequency equal to 2 pi or the sampling frequency equal to 1 unit, then you don't have units because you're dividing when normalizing by the sampling frequency. Okay, so that's the question for Krishna. I hope that clarifies your question. Now let me take Sharada Avula's question. Good evening, sir. Kindly check 5th question in assignment 6. I tried many times and couldn't get any of the answers given in the question. I think there is a negative sign. Okay, we will do that. Right, so I have my friend sitting here, Aniket Sadashiv, and he will check. And in fact, they propose to have a session with you. Is that right? So Aniket and his friend, my teaching associates are going to have a session with you to discuss some of the questions and their solutions. Okay. Now, let me take Krishna Koneru's question again. There's confusing notation. Yeah, I agree with you. Actually, if one wanted to be very fastidious about notation, then capital H e raised to the power j omega is the most correct notation because, it's really a special case of the Z transform. However, what we do is that, we often ignore the fact that, it's e raised to the power j omega and we just think of it as a function of omega. So I would say I agree with you in some sense. It's a misuse of notation just for simplicity. H of j omega is not, either we should write H of omega or we write H of e raised to the power j omega. H of j omega would not really be correct. That would only be for analog frequencies, right? Not for digital frequencies. Now you have to be careful. When you're doing filter design, you're dealing with the analog domain frequency and the digital domain frequency. So in fact, there you notice we used 2 different symbols for them. We used a capital omega symbol for the analog domain frequency and a small omega symbol for the normalized digital frequency. That we should be careful. Now, one should not confuse the normalized frequency in the digital domain for the original analog frequency with which we are working. Right? So that omega H of j omega is not correct. Okay, so Sharda says 4th question in assignment 6. Okay, so I think my teaching associates will look at these questions, right, and then figure out. In fact, they will so maybe you should have a session with them, and explain some of these solutions and correct if required, right? Correct something if required. Now, there's one more question from Krishna Koneru. Frequency is also termed as rate of change of phase. But I thought frequency and no, wait. See, the instantaneous phase and the starting phase are 2 different things. When we say phase of a sinusoid, we're talking about the starting phase, the phase at a particular time reference, right? Instantaneous phase changes as time progresses. That's why you get a frequency. So frequency is the rate of change of instantaneous phase. But the starting phase is what determines how different sinusoids are placed relative to one another in terms of their initial situation. Okay, that's what one should. So in that sense, starting phase and instantaneous phase are 2 different things. Okay, wonderful. Now let me, while we wait for Satish Kumar tell us more subjects where he wants us to justify their presence. Yeah, we'll wait for others also to put up questions. And meanwhile, I have a question from, let's see the Google sheet. There's a question from Tilak. Yeah, there's a question I see from, yeah. He says he's from industry. Well, we are right here. We are interacting with you. We would like to interact with the professor. Well, I'm right here, Tilakji. Are you here? If you're here, then we can talk. Yes, I do believe we got your email. I've responded to it. But if you should be here today, and we can talk. And then I see KG Krishna also. Huh? Concept of, what does he say? He
Yeah.
says concept of frequency, Krishna Koneru, I think. On x-axis, 0 cent. I think that's the same question. Great. Wonderful. Next question. Or next comment, whatever. Maybe you can all share, all of you who are here, can you share are you able to understand the lectures broadly? Do you find yourself listening to them attentively? Can share your experience in using the lectures and the assignments and so on. So can we see how many people are in the chat right now, or how many people are online? I think we can't see it here. Okay. So we see 8 people are on the. So why don't we? Yes, Satish Kumar. Okay. So what about the others? We've heard from some of you. We'd love to hear from the others as well. So anyone else who has anything to share that we can respond to? Okay, I have a question from Sharda. Are FIR filters without linear phase also exist or FIR means by default? No, FIR filters do not necessarily have to have linear phase. In fact, when we design multi-rate systems, we design 2-band filter banks to construct the discrete wavelet transform, for example. The wavelet, the Dobeschi family of filter banks, except for length 2, none of the others have linear phase. They cannot have linear phase, right? So if you have a 2-band filter bank with perfect reconstruction, and it has FIR filters, they cannot have linear phase after length 2. That can be proved, which means that you have to do away with linear phase if you want what is called orthogonality in the filter impulse response to its own even shifts. So no, the answer is no. You don't have FIR filters do not necessarily have to have linear phase, but FIR filters are capable of giving you linear phase. That's the way you should look at it. See, there are no analog systems which are capable of giving you linear phase. That is the beauty of digital signal processing. Only digital FIR filters can give you linear phase. Right? That's the idea that You must understand. Now, Krishna Kuler was asking me, do we have to remember all Laplace transform, FT, Z transform properties while answering questions? Well, are these interrelated? Can we get a comprehensive cheat sheet of properties? I would recommend, I know that the properties, well, you at least need to remember some basic properties. Otherwise, what happens is each time if you're going to try and analyze, a solution to a problem, and if you're going to have to refer to a cheat sheet for properties, it's not. You don't have to memorize all the Z transform. That is not required. But you do need to understand some properties. You can relate. Actually, many of the properties can be derived with a little bit of work if you practice. So my recommendation is, it's a good idea to get familiar with the properties. It's not a good idea. We cannot provide a cheat sheet. And if necessary, of course, in the question, one might provide certain hints, which will give you an idea of which property is being invoked, if that's required. Right? But otherwise, I think it's a good idea to master the properties. Yeah. Okay, good. So cheat sheets, unfortunately, we won't allow in the exams. Because there's no uniform way of enforcing. Of course, whatever data is required is provided in the question normally, right? If there is some such data required. Okay. Okay, I have a question from a new member now, Dibi Sahu. What are the chances of getting PhD under you if I top the exam? Wow, if you top the exam, definitely then you have a good chance, I'm sure. So Dibi Sahu, you should tell us, where are you from? What are you doing? For PhD, you have to come through our admission process also. I hope you'll be applying, So, Dibi Sahu, you can tell us, where are you? What are you doing now? And, you have to apply for the PhD program, right? I would say, tell me more about yourself. And, if you're really keen, then we can certainly talk further to see if, you will be able, if you will be happy doing a PhD with my supervision. If that's going to be a source of happiness and satisfaction, and, also, you have to feel that you'll be able to do it. So then we have to work that out, right? So tell me more about yourself. We can also take this discussion offline, and and of course, if you think that, you will be able to find something which you can do with my supervision, I'm sure it should be possible. Okay, let me see. Sharada's question. Discrete sync signals DTFT does not exist, but can we find the Z transform of discrete sync by properly choosing the ROC? Okay, good. I understand where you're coming from. See, the DTFT of the discrete sync signal, in some sense, the discrete sync. Now, see, if you take, let's go this way. Take, for example, the ideal low-pass filter, right? The ideal low-pass filter. The ideal low-pass filter, the inverse the impulse response of an ideal low-pass filter is a sampled version of a sync, isn't it? It's a form sine omega Cn by pi n. So the ideal impulse response of a low-pass filter is an example of a discrete sync. Okay, so it's not really correct to say that the discrete sync DTFT does not exist. Yeah, it exists, but it has a discontinuity, right? And in fact, the problem goes to taking it to the Z domain. So if, as you say, as I think where you're coming from is, you're saying, if you're talking about the DTFT of the discrete sink, then ipso facto it should have a Z transform, because you're defining the Z transform on the unit circle, so it should go at least a little beyond the unit circle. You're right. See, you have to then extend the idea of Z transforms to discontinuous complex functions. So you can think of discontinuous complex functions, right? See, otherwise, the Z transforms that you encounter typically are all continuous analytic complex functions. But then you have to also allow for discontinuous, more general complex functions. And then you can also include the ideal filters as examples of such, okay, to calculate the Z transform and so on. Now, if there, the concept of region of convergence has to be understood in a little broader sense. Naturally, when you talk about region of convergence, it applies most meaningfully to rational system, rational Z transforms. In irrational Z transforms, like what you have in the discrete sink, you do have to think of region of convergence, yes. But the broader way of looking at it is there a set of points in the Z plane where this sum converges? So for example, if you take the discrete time Fourier transform of the sample sink, at the point of discontinuity of the low pass filter impulse response, there's no convergence. On the other hand, if you truncate that sink and try to calculate its discrete time Fourier transform, it will start exhibiting the Gibbs phenomenon, right? It would show an analytical expression, but it would start exhibiting the Gibbs phenomenon. So discontinuity is always a problem. So, it converges everywhere else, but it would not converge the discontinuity. Some of these ideas also come from the Fourier series expansion. In fact, there's an intimate relation between the Fourier series expansion, what you're seeing in the discrete time Fourier transform. The discrete time, in fact, the Fourier expansion of the discrete time Fourier transform is the inverse DTFT. Think of it that way. And therefore, at points of discontinuity, you're going to run into trouble in convergence. Okay. Now, I have Krishna Koneru asking, his intuitive understanding of the impulse signal is it generates all frequencies in frequency domain. Yes, you're right. See, in fact, let me ask you to do the following experiment. Take or start adding up all sine waves which are, with the same starting phase of 0. So take cos omega t for different values of omega. And now, you can do this experiment. You add up cos omega t over a large range of values of t, including 0, and, take a fine grid of omegas, frequencies, fine grid of frequencies, and add them up over a large range of the time axis, taking many of the frequencies. You'll slowly start seeing that there is constructive interference only at t equal to 0. Everywhere else, slowly you will see destructive interference. Okay, so that's the way to understand this impulse function from the frequency perspective. All these sine waves of 0 frequency come together to give you an impulse. What does the impulse have? All these sine waves constructively interfere as t tends to 0, which means they maintain, you can also verify that they will maintain an area of unity while the width starts becoming 0, right? So you have non-zero area compressed into so-called 0 width. That is the idea of the impulse. Now, Dibi tells me, yes, he's a final year MTech student of optoelectronic and laser technology. He has qualified GATE and NET. Dibi, optoelectronic and laser tech, I'm very happy to know that you have done these subjects. No, I work in signal processing and particularly in multi-resolution signal processing. We'll have to see if there's something that, which your training gives, which will interest you in doing a PhD with my supervision. So maybe we should discuss that offline. You can send me an email and I'll be happy to see what you're writing. Yeah. So you know my email. I'll just type my email in the chat. Maybe you can just type it VMGADRE. So I'm typing my email in the chat, vmgadre@ee.iitb.ac.in. So Dibendu, is your name Dibendu or something? Yeah. So maybe I've just put my email in the chat. I think all of you can see it. So that's my email. You're very welcome to write to me. To introduce yourself and give reference to this discussion here. Do you see the email, Sahu? Sahu, did you see the email address I put up? So then if you please confirm and then write to me, right? And tell me more about yourself. And we can also have a video conversation if you want that on Google Meet or something. Unfortunately, I can't unmute you or ask you to talk today, but we can, yes, yeah. So we could have you can work out a separate Google conversation, Google Meet conversation. Very nice. So further questions or comments or? So any further participants, questions, comments? Okay, we still have 8 viewers. I'm hoping that some of you 9, we've now 9 viewers. So I'm hoping that some of you still have some questions or something that you would like to share with us. Yes, let me see what Krishna Kuneru was asking. A filter means it keeps amplitude of certain frequency intact with zeroing. Yes, so can we have linear? Yes, you see a filter, let me explain. Now, a linear shift invariant stable, actually not even necessarily stable. A linear shift invariant system with a frequency response, which means the impulse response has a discrete time Fourier transform, which is expressible, is called a filter. Right? I mean, in the sense of, see, the word filter is also sometimes used more broadly. So there are also people talk about non-linear filters. There are median filters, there are, so this is a more, so a filter is used more, the word filter is also used more generally to represent the process. The filter as a verb means remove certain things that you don't want. Filter as a noun refers to a system which does that. Now, one primitive understanding is as you said, ideally remove certain frequencies that you don't want and retain frequencies that you want. But as you said, that's not necessarily the most general way of dealing with what you want to do and what you don't want to retain. You may want to give different weightages to what you retain. As you said, you can have a linear part of the frequency response. That will also be a filter, yes. So you could have a filter which is not piecewise constant. In fact, when I talk about filter design, I've emphasized that all the design strategies that we are talking about here are for piecewise constant filters. Filters don't need to be piecewise constant in their ideal response, right? Now, Sharda has a question. In IR design, how can we justify that, like either in Butterworth or in Chebyshev filter designs? How can we say we are taking infinite samples of impulse? You see, the impulse response being infinite does not mean the filter requires infinite resources. Let's be clear with that. The impulse response being infinite can also be the consequence of a filter with a finite realization. And only such filters are of any use to us, right? Only filters which can be realized with finite resources, which might have an infinite length impulse response, are of use to us. So the way to understand this is, if you have an infinite length impulse response, if it corresponds to a rational system, then it can be realized. Otherwise, it cannot be realized. It cannot be translated into a hardware or software implementation. So there's a difference between the impulse response being of infinite length and unrealizability. You can have realizable impulse responses which are of infinite length, like the impulse responses of the Butterworth filter or Chebyshev filter. I hope that clarifies your question, Sharada. Also, you might want to ask why these two particular filters. See, the Butterworth and Chebyshev filters have some kind of optimality. The Butterworth filter, for example, has a monotonic response. So it's a simple response, a very simple kind of response which monotonically decreases with frequency for the low-pass filter, or decreases from the center frequency outwards. The Chebyshev filter, on the other hand, is much more economical in its use of resources when you're talking about the magnitude response. But the phase response has to be compromised in comparison, between Butterworth and Chebyshev. Very good. So, do we have more questions, comments? So we have 6 viewers now. Do any of them have anything to share or ask? Okay, let me see. Satish Kumar has a question. Can we differentiate analog components and digital components just by seeing the components? Yes, for some of the components. See, some of the analog chips and digital chips look very similar. If you take an operational amplifier chip and you take a simple gate, they appear similar when you look at the chip level. They look very similar as chips. But one of them is essentially analog component, the analog, the operational amplifier. And the gate is essentially a digital component. So just by seeing the components, you may not always be able to distinguish analog from digital. In some, well, analog discrete components can be distinguished. So, the resistor, inductor, capacitor, the transistor, the diode, these can be clearly distinguished. But then, if you're talking about chip level, the chips don't necessarily allow for distinction simply visually. Okay, Krishna Konoru is asking, in all our discussion, we assume sampling frequency is constant. This cases, do we have multi-rate within the same signal? Yes. Well, there are two different things. You could have a system in which different parts of the system work at different sampling rates. This is called multi-rate signal processing. That's a subject by itself. So you can very well have that. In fact, normally, if you do have that, you would have the sampling rates being rationally related. So there is a so-called least common denominator of all the sampling rates, and that is the highest sampling rate you need to work with, and all of the others are fractions of those, right? So one can build up the whole subject of multi-rate digital signal processing builds up from multiple sampling rates in the same system. If the sampling rates are not rationally related, then the problem is much more complicated. It's difficult to analyze such systems. These kind of questions are addressed in control, but the analysis is far more complicated. But if all the sampling rates are rationally related, and in fact such systems are very important in digital signal processing, they form the basis of what is called multi-rate digital signal processing, subject by itself. But now, I think your question is, could you have different sampling rates at different points in time? In principle, you could, but the analysis is non-trivial. So, the analysis of such signals where you're sampling at different rates at different points in time is non-trivial. Okay. Any other questions? We have 9 viewers now. Oh, I'm sorry. 8 viewers. 7 viewers. So we have reduction of viewers now. Any other questions? Okay, looks like there are no questions that I can see coming up, or no discussions that people want to have. So then I guess we have to terminate this. We have to conclude this, not terminate, but conclude this session. Yeah. So a very good evening to all of you, and hope to see you again in a subsequent session. Aniket was also very happy to be with me this evening. And he's also, I think the teaching associates are planning a session with you, right? They're going to record some sessions for you. Very good. To solve some of the assignment problems. So very good evening to all of you. Okay, one fun question, very good. Which one was invented first, Laplace transforms or signal processing? Laplace transforms. Laplace transforms are much older than signal processing. So, Laplace was a mathematician maybe about a few centuries ago. And the contributions of Laplace are much more than what we see in signal processing. There are so-called differential equations which are, which emerged from Laplace's investigations. So in that sense, Laplace transform is just one of the things that he's contributed. Or you could say, maybe he never called it the Laplace transform, but, he certainly saw that idea of converting differential equations into algebraic equations, but he did much more than that, right? Laplace, as a mathematician, contributed much more than the Laplace transform. Yes. Okay, good that we had a fun question. Or no, I won't say fun, it's an interesting question, certainly. Should we then conclude the session if none of you have any questions or discussion? Okay. 5 बजे तक था ना? Okay, fine. Okay. Thank you. Yes, thank you, Krishna Koneru. Yes. All right. I guess we have to conclude. I believe there might be some other session also coming up. No?